shout out what's wrong with this. Mutable default, exactly right. So when you can see the call me there, you call it, and it looks like it works exactly right. If you've appended foo onto the end of the list, everything's great. However, if you call the call me function without any arguments, the default argument is used. The default argument is created at object creation time, not instantiation time. So you can see that 2 calls to that, the same object is used, so it's appended to the list. Again, depending on how this bug primitive is used, it can be very useful. I've seen some lists like this where socket objects are defined, and you can get access to a different socket object and take over a session. Again, not a bug that most kind of Python developers would really be too aware of. And there's a ton. I mean, there's a whole nother talk on ripping Python to pieces. When you start to look at the code and start to look at other people's applications, you can get some pretty cool bugs. So that was the why are we doing this. What were the initial aims? What were we trying to achieve with this? Well, really want to have as rapid assessment and targeting of bugs within Python code as possible. You want the toolkit to highlight where are the areas that you want to look at and to really pull those out for you. Obviously, we've talked about the information layer rather than the data layer. We want to get source code back. We don't necessarily want to get a full disassembly. We want to get source code. We want to see what that guy wrote, how he approached things, where are those bugs going to be. And obviously, the motivation for this was there was some anti-reversing techniques that were in use. We want to get around them, but it would be nice not to have a specific block for each technique, have a more general approach that is usable against all the techniques and the assumptions that those techniques make. So that's the aims that we're going in with things. Now, obviously, we're going to have to talk a little bit about some of the lower level language. I don't know how familiar people are with Python, so we'll blast through this if it's familiar to people and they already know it. I apologize, but without it, some other people may be completely lost if they haven't seen this before. So there are a few different standard file types with Python. Obviously the .py, which is what's written in the source. Sorry, where the source code is written. That's human readable. It will run on any Python supported platform. Lots of open source products are distributed in the .py format. Obviously, you can compile this through to a bytecode representation. The standard bytecode representation is pyc. I'm sure you're all familiar with those. Created by compiling or upon import, which is an implicit compile. It's nothing to do with speed of execution, purely speed up of instantiation. It's the startup time of, if you've already got the pyc there, you don't need to go through the compile step. It is cross-platform bytecode, so you can compile it on Windows and use it on Linux or Mac, but it's not cross-version. They reserve the right to between Python 2.4, 2.5, 2.5.2 to change the bytecode up so that one bytecode compiled with one version of Python won't be executable by the other version of Python. We're going to have a little look more of that in a second. And they do purposely undocument it to allow them to have as much flexibility with changing up the format of the pyc as possible. It's not a particularly complicated format. We'll look at it. But it is undocumented so that people don't write a bunch of libraries that depend on this particular format and then they all break when they change the pyc format. PYO is essentially the same as pyc, but it's optimized. One level of optimization, it will have its asserts removed. 2 levels of optimization has the asserts and the inline documentation removed. Most of the time, this makes no difference. It just reduces the size of the bytecode. And now and again, if there's code which uses the doc strings, an example being Python, Lex, and Yak, the grammars are encapsulated in the doc strings, then if you compile to PYO, you completely blow apart the application. It doesn't work anymore. So there is a few gotchas in there. And PYD is the most complex serialized format that Python deals with natively, and it's called a frozen format. This compiles the Python into C-shared objects and allows it to be distributed without having to have the Python runtime there. There's been a great discussion by this with antifreeze, which was a tool presented at Recon, I think 2 years ago now. Aaron Portnoy and Ali did a great tool to be able to easily access the internals of a PYD and change the bytecode within, recompile the PYD, and then use it. They had some funny demos with with some games that were developed in Python. PYD is a very popular format when Windows is being used for the target platform, and you'll see a lot of people distributing in PYD, assuming that that kind of contains all their intellectual property, no one can get access to it. So a quick look at the PYC format. It's very simple, as I said. It begins with a 4-byte magic number. That magic number is to do the version check. So as we said, different versions of Python work with different, have a different magic number, and they know what number they're supposed to work with, so they won't execute another set of bytecode from a different interpreter. There's also the OXOD OA bytes in there to purposely break the bytecode if that bytecode file's been accessed in a text editor or something, because it will affect the OXOD. Then there's a timestamp. The timestamp's used to know whether the PYC needs to be regenerated. If there's a PY and a PYC in the same directory, and the PY and the timestamp on the PY doesn't match the timestamp embedded in the PYC, then the PYC will be regenerated because the PY could have changed, obviously. So it's an equality test. It's not a greater than or less than. And then after these 8 bytes, there's just the marshaled code objects, which are code objects from Python, which we're going to look at, serialized out. And obviously there's packaging technologies, pyToexe, pyToApp, CX freeze, etc., which allows people to bundle their code along with the runtime into one big ball, which makes distribution easier. It's used a lot. It allows, the biggest thing it allows is developers to have a modified runtime which they develop, which they release with their code, and we'll look at all the modifications which they put into their runtime to try and avoid people being able to reverse the PYCs back out. So object hierarchy. I'm sure most of you know this, but this is kind of how things stack up in Python land. There's a module object. The module object doesn't have any top-level code object. This is done for performance reasons. It's highly annoying when you're trying to reverse things out. We'll go into the ways to get around this, but there is no code object at the module object layer. Within a module object, obviously you can have classes. The superclasses are kept in the attribute underscore bases. Classes have methods. Methods have a function of im_underscore func, which holds the function object. The function object has a function code object, which holds the code object, and this is what we want. So it's kind of a big onion, and you have to peel it back. Eventually, you get back to a code object, which is a representation, and it's quite a verbose representation of the bytecode, variables, run state. It can affect the framing. We won't discuss framing today because that will be another 40 minutes. Some of the attributes within which you can see the CO code attribute is actually the string representation of the bytecode, constants names, files names, where it's from, the line number in the source code which this object was from. Now, just to be clear, not everything has a code object. Functions have code objects, generators have code objects, methods have code objects via the fact that they've got a function object within them, but not everything has a code object. So there's some level of reconstruction that we have to do when we can't find a code object for a certain type of object. Oh, wrong way. So that's the stack of the objects. Now, obviously, Python has some kind of like bytecode, some opcode language, kind of like x86, but very, very much simpler. The opcode got pi represents this at the Python runtime layer. It's just a list of bytecodes, a number and the mnemonic which it maps to. All opcodes are 1 byte, so there can only be 256 of them. Currently, there are 113 defined, so there's lots of space for improvement. Optionally, an opcode can have arguments, or an argument. All arguments are a 2-byte argument. The opcodes which have arguments are just specified by an attribute which has argument, and it will say the value of the opcode, which is above which all opcodes have arguments. So it's just 2 bytes, and obviously how those 2 bytes are dealt with by the argument is down into the AST layer. So if we have some Python source, which is just print bugs, if we disassemble this is just disassembled with the dis module from Python itself. You can see the bytecode instructions which are there, and the 2 instructions which have arguments. And if we look at the, actually look in the code object, the co underscore code object, these are the bytes which come out. Obviously, you can see the 6.4 represents load const, 4.7 for print item, etc., etc. So it's a very, very simple representation of a language. So we've blasted through, this is how Python works, this is what it looks like, this is a code object, this is how everything stacks up. What tools exist currently for reversing Python? General categories, obviously it's disassemblers. Dis.py comes with Python as standard, it's just a stdlib module. You can pass in code objects or higher level objects, and it will give a representation like we saw a couple of slides back of the instructions and their arguments. This implicitly relies on opcodes.py, which is also obviously a standard library module. It looks to opcodes.py for those mappings. So it's looking through the byte stream and it finds each byte and then it refers to opcode.py to be like, what does this represent? What am I going to do with this value? There's some debuggers. PDB is the standard Python debugger. It is very extensible. It itself is extended from BDP, but it's very much a debugger which is oriented for when you're developing Python code and you've got a bug, where is the problem, rather than you've got a closed binary and you want to work out what's in there. So it's a developer aid, not really a reversing aid. But it's a good basis upon which to apply other stuff. And a lot of the things, a lot of the functionality which it exposes relies on it having access to a .py file, which from a development point of view is perfectly reasonable for a debugger to assume that it's got access to the source code. Obviously from our point of view, that's not necessarily true. There are some decompilers, varying quality of decompilers. They will take an object such as pyc or a pyo and take it back to source. They'll take that file from disk and reverse it out through the understanding of the marshalling format and the code objects. They will go back and give you some source code back. There are free ones, there are commercial ones. Some are applications, some are online services. I'm not sure why anybody would use the online service and submit all their source code, but some people do and also pay for the privilege. There are dpython is an online service. It tends to be very, very good. Decompile is an old one. It's good for Python 2.4, but it hasn't really kept up with some of the newer stuff. unpyc is a free tool, a free product application, which is pretty good. It's not perfect, but it's good enough. That's the one that I use to extend a lot of stuff into in pyREtic. And there's also bytecode assemblers and modifiers. Antifreeze would fall into the modifier category, but there are also byteplay and bytecode assembler, which are just general Python utilities to work at the layer of building up things from opcode, so from the bottom up rather than writing Python source code and having it compiled down. They do allow the modification of live objects through some various hacks. If people are interested, I'd certainly byteplay's pretty interesting to look at. They've done some cool stuff there. So, if that's all the reverse engineering tools that are available, obviously everybody, all the people that are authoring code can see what those tools are. What are the techniques that they're using to stop people reverse out? Obviously commercial and closed source applications, they want to develop in Python because of the speed and the ease and the cost efficiency and the cross-platformness, but they don't want everyone to look at their code. So they've come up with an increasingly number of techniques coming out with them trying to stop you being able to peek at the code. Obviously some of the applications we were looking at had this, and this is where everything began. A high-level observation is all the techniques that we've seen really rely on trying to obfuscate the pyc and pyo